kinetics of radioactive decay. First, I'd like to point out radioactivity is natural. It's not man-made. It's not something we've done to the environment. It's a natural component of our environment. Are all natural things good and healthy for you? No, they're not. Just because something's natural doesn't mean it's safe. Radiation is natural. All elements that have more than 83 protons and some of the others are unstable. They are radioactive. The reason that we still have radiation is that radioactive nuclides are constantly being formed, and some of the ones that were existing in the beginning, whatever that was, decay very slowly. Very is an understatement there. Like billions of years, right? And so they just have not all decayed yet. Radioactive decay is always first order. So first order rate law, the rate is equal to a rate constant times, in chapter 14 we looked at concentration. Here we're looking at the number of nuclei. So how many nuclei? The rate is going to depend on how much stuff there is. Some nuclides have very large rate constants, some have very small. And we also talk about a half-life. We talked about half-life with rates of reactions. A half-life is the time for 1/2 of the original substance to decay. So it's the time for half of it to go away. And this is the same equation we had before. T1/2 is 0.693 divided by the rate constant. So nuclides that decay quickly have very short half-lives. T1/2 is small, and that means that K is large. Those are considered very active. There are a lot of decay events per unit of time. Nuclides that decay slowly are going to have a long half-life, a lower rate constant, and there may be very few decay events per unit time. And so that's the Schrodinger's cat experiment, where you've got a sample of radioactive substance in this chamber with the cat. And you don't know when one of those nuclei will disintegrate and trigger the Geiger counter. You don't know if that's happened until you open the box. And then you find out, is the cat dead or is the cat alive? So here's an example of kind of two extremes. So thorium-232, the half-life is 14 billion years. It would take 14 billion years for half of it to decay. So if you started with 1 million atoms, is 1 million atoms very many? No. A mole of atoms is 10 to the 23rd, and that you can generally hold in your hand, right? Small quantity. So 1 million, after 14 billion years, you still have 500,000. And then after another 14 billion years, now you have 250,000, right? It's going to take a really long time for all of that to disintegrate, right? It's important to note that the radioactive sample does not decay to 0 atoms in 2 half-lives. It's just that it gets cut in half with every half-life. And so it's exponential. It is not linear. So that one has a really long half-life. 1 million radon-220 atoms, that has a half-life of 1 minute. So if you start with 1 million radon-220 atoms, in 1 minute, in 1 minute's time, it's gone down to 500,000. And in another minute, it's down to 250,000. In 10 minutes, you're down to 1,000 atoms. So that stuff goes away pretty quickly. Right? So here's a graph of atoms of radon-220 over time with the T1/2 of 1 minute. So if you start with 1 million, after 1 minute, you've got 500,000. After another minute, that's down to 225, etc. And so as you get closer the rate goes down as you get fewer and fewer atoms. Yes?
Half-life goes up with half of the sample that you have.
Yes.
Decaying. So really just using half-lives, you'll never reach 0. When do we call it 0?
That's an excellent question. When would you call it 0?
It's a half every time. You know, like we can close the distance half, but you can always close the distance half. So
until you get down to 1 atom.
Okay.
Right? You get down to 1 atom, and then you can't get down to half of an atom. So it does get to 0.
Yeah.
Because there is a smallest piece. Practically speaking, it would probably be considered 0 when you couldn't detect the radiation anymore, or when the amount was too small to measure in any way. It kind of depends on the purposes. You might also say, well, we're going to consider this to be 0 when the level of radiation being given off here is the same as in the general environment. Yeah. Here's just selected nuclides and their half-lives. Radon-220, 55.6 seconds, and then some of the rest of these are really, really large. And then thorium-219, 10 to the minus 6 seconds, a microsecond, right? And then some of them are alpha and some are beta decay. So the integrated rate law gives us this relationship. The natural log of the concentration at time t over the concentration originally is equal to negative kT, where k is the rate constant. So for radioactive decay, we're not talking about a concentration. We're going to look at the number of nuclei. So we'll say the natural log, the number of nuclei at time t over the original number of nuclei is equal to negative kT. So same equation, but number of nuclei instead of a concentration. Okay, so plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for a 1.35 milligram sample of plutonium-236 to decay to 0.100 milligrams? Well, we're given the half-life, right? T1 half is 2.86 years. And then we also have this equation where the natural log of NT over N0 is equal to negative KT. And we're trying to find a time. How long will it take? Well, this has number of nuclei in it, and here this is masses of plutonium. Do we have to convert this to number of atoms? No. Converting milligrams to atoms would involve using Avogadro's number, right? We'd be multiplying by Avogadro's number, but we'd also be multiplying this one by Avogadro's number, right? And so Avogadro's number is going to cancel out of the equation. If you're dealing with the same element, then the mass is proportional to the number of nuclei. If you're looking at two different elements, then you have to worry about it. But here it's plutonium and plutonium. So we can say that the natural log, the amount of plutonium at the end that we're interested in is 0.100 milligrams. And starting, we had 1.35 milligrams. Those units cancel out. But over here, we need to know what the rate constant is. We can calculate that from the half-life. The rate constant equals 0.693 divided by the half-life. So minus 0.693 divided by the half-life of 2.86 years times t. So we got the natural log of 0.1 divided by 1.35. I'm going to multiply by that denominator. I'm cross-multiplying, and I'm going to divide by 0.693, and I'm going to change the sign, and I'm going to come up with T equals 10.7. What are the units on T? Years. So this thing here, we've got T1/2 in the denominator. The unit there is year, and so the year is the unit on time. If you had this in minutes, then T would be in minutes. If you did it in seconds, it'd be in seconds. So it would take 10.7 years for that 1.35 milligram sample to decay to 0.1 milligrams of plutonium-236. Any questions? Integrated rate law. So we kind of did this just now. Since the mass is directly proportional to the number of nuclei and the integrated rate law has a ratio, we can use initial and final masses instead of numbers of nuclei. So we can also express it with masses or with the rate of decay. So you can look at the rate of decay, the mass, or the number of nuclei. Radiometric dating is a group of techniques that uses the predictable decay of radioactive isotopes present in the environment to estimate the age of rocks or artifacts. It could be fossils, old things that have those isotopes in them. So one of those types is radiocarbon dating. And this was devised in 1949 by William Libby. He was at the University of Chicago. Not all of these discoveries were people in Germany or Sweden or something. There were a lot of Americans that did some cool things too. It makes use of a radioactive signature resulting from the presence of carbon-14 in the atmosphere. So he got the Nobel Prize in 1960 for this. And this is a technique used by lots of scientists interested in old things, archaeologists, geologists, anthropologists, etc. Pardon me?
The ground people.
The ground people. People are looking at stuff in the ground, yeah. An example here, the Dead Sea Scrolls. It's kind of an interesting story. 1947, some young shepherds in Israel were looking for a goat that got away, lost goat. And so they went into a cave near the Dead Sea, and they're looking for this goat, and they found ancient scrolls stuffed into jars, right? It's like Indiana Jones or something. And so how do you know how old the scrolls are? Radiocarbon dating. They used radiocarbon dating, and they determined that these were about 2,000 years old. They were texts of the Hebrew Bible, and these were about 1,000 years older than any of the other texts that were currently known. So this was a big deal. They're called the Dead Sea Scrolls.
I think they just found some more pieces, too.
They found some more pieces? Yeah, I wouldn't be surprised. There are also things that have been disproved using radiocarbon dating. Your book talks about the Shroud of Turin, which people thought was the actual shroud that was wrapped around Jesus when he was buried. But radiocarbon dating shows that it dates to like the 1300s. So, probably not. So how does radiocarbon dating work? Well, carbon-14 is formed in the upper atmosphere. So we've got neutrons bombarding nitrogen, and that generates carbon-14. Well, carbon-14 is radioactive, and then it decays back to nitrogen by beta emission. It has a half-life. Oh, I forgot to change that one. This apparently has been updated as well. Your book now says 5715 years. Half-life is 5715 years, so 5,715 years. So this is happening in the atmosphere all the time. There's continuous formation and continuous decay, and those are in equilibrium. And so in the atmosphere, the amount of carbon-14 is nearly constant. Any fluctuations are not very significant. So what happens to the carbon-14 in the atmosphere? Well, same thing that happens to other carbon in the atmosphere. It gets oxidized to carbon dioxide. Plants take that in through photosynthesis and incorporate it into themselves. And then things eat the plants, and it makes its way up the food chain. So any living organism is continually taking in carbon-14 and losing it as well. So the level of carbon-14 in that organism is going to be the same. We look at the relationship, the ratio of carbon-14 to carbon-12, which is a stable isotope. Well, when something dies, it stops taking in new carbon. Whatever carbon was in it when it died, that's what's in it now. And the radioactive carbon-14 continues to decay. And so as that dead thing ages, the ratio of carbon-14 to carbon-12 goes down. And it goes down in a predictable way because we know the half-life of carbon-14. So every 5,715 years, the amount of carbon-14 gets cut in half. So this is something that, I should have gotten this earlier in my education, I suppose. But it was probably, 5 or 7 years ago. I was lecturing on some biochem stuff, and it just suddenly hit me. Have you ever wondered where plants get their substance from? You go plant a seed, and it grows, and maybe it becomes a big tree. Where did all of the matter that's in the tree come from? Did you ever think about that? Does it come from the ground? Is there a big pit where the tree grew? I mean, matter can't be created or destroyed, right? It comes from the air. It's the carbon dioxide in the air. Plant takes in carbon dioxide and uses that carbon to make cellulose and build itself up. Is that crazy? It's absolutely crazy. It just blew my mind right there during lecture. It was crazy. So I thought I'd just, pass that on to you. Okay, so there's a limit on how old a thing can be. The maximum age that we can estimate is about 50,000 years. And the reason for that is that after 50,000 years, the amount of carbon-14 left in that thing is so small that we can't reliably measure it. We're not just using this ratio. We can check it against objects whose ages are known from historical sources. So, you've got this object that's been documented, you know how old it is, and then you can compare ratios to that. And what they found is that there's deviations of up to 5% in atmospheric carbon-14 levels over time. But that's pretty small. They've also done some corrections and extrapolation using data from western bristlecone pine trees. So these things can live like 5,000 years. And so you can look at the rings and find out how old the tree was. And so they can fine-tune some of the dating using that as well. It's especially cool if you can get a tree that died a long time ago and a living tree that overlapped. They were alive at the same time. Then that helps you to get back even further. So that's pretty cool. Okay, so here is a practice problem. Researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that's 89% of that found in living organisms. How old is the scroll, and could it be authentic? Or is this guy just lying to us? Well, what's the half-life for carbon-14? 5715 years. And we've got this relationship, the natural log of whatever measure we're using, we'll just call it n, nt over n0 equals negative kt. So here we have the half-life. From the half-life, we can calculate the rate constant. The rate constant is going to be 0.693 divided by the half-life. And you can write all that out, but I just prefer to write it as 0.693 over 5715. What's this 89% going to tell us? Yeah, it tells us the amount now compared to the amount originally, right? So if we're at 89%, it must have started out at 100%, right? So 89% is telling us the ratio of NT to N0. So we could say that it is 89 out of 100, or we could say it's 0.89 out of 1. Okay? That's what's left. So we've got the natural log of 0.89 being equal to negative 0.693 over 5714 years times t Oh, I see what I did wrong. There we go. 961. Does that date from 500 BC? No. If you take 2018 minus 961, $10.57. Yeah, doesn't even get you to 0. So this guy's, trying to pull one over on you. Any questions? So carbon-14 isn't the only sort of dating that can be done. Uranium-lead dating. I don't know, this just suddenly struck me that this is uranium and lead going out on a date. Sorry, uranium-lead dating. So radiocarbon dating, the thing had to be alive, right? So if you're looking at a rock or something that was never alive, you can't use carbon-14. It just doesn't work. But you can look at the ratio of uranium-238 to lead-206 and get an estimate of age that way. So uranium-238 ultimately decays to lead-206. And so we can compare how much is left of the original amount of uranium-238. And that's we find this especially in igneous rocks. And so those rocks were once molten and they solidified. And once they solidified, nothing's going in or out of them. The uranium that's stuck in there is stuck and it's just going to decay. The half-life for this decay all the way to lead-206 is 4.5 times 10 to the 9 years. And so this can allow some pretty old dating. We can tell that it's lead from radioactive decay rather than just naturally occurring lead because it has a different isotopic composition. So if you just, find lead, it's not going to be lead-206, right? It's going to be a mixture of isotopes. Okay, let's do an example here. A rock contains lead-206, lead-206 to uranium-238 mass ratio of 0.145 to 1. Assuming that the rock did not contain any lead-206 at the time of its formation, determine its age. So T1/2 is 4.5 times 10 to the 9 years. So we could figure out the rate constant for that. That would be the rate constant. And we're going to use that same equation. So we got K. Now we need to find NT and N0. Can we just use this ratio and do 0.145 over 1? This is a mass ratio of lead to uranium. Is the mass of lead is proportional to the number of atoms of lead, but is that proportional relationship the same as for uranium? No, because they have different molar masses. So what do we do? Well, let's say that we've got 0.145 mass of lead-206. We can choose our mass unit because it's a ratio. What do you want to use? Maybe grams? So 0.145 grams of lead-206. And we want to figure out something related to the particles, the number of particles. So it could be moles, right? Or we could go all the way to atoms. That gets a little obnoxious, though, because you've got these huge powers of 10. So maybe going to moles would be good enough. So if I want to know how many moles of lead-206 from grams, I need a molar mass. 206. So on the periodic table, the mass of lead is 207.2. But that's the average of all the isotopes normally occurring. This is lead-206. Its atomic mass is very close to 206. So that's going to be good enough. So this will get us moles, and then we can compare moles. So divide by 206. 0.000704. Keep through sigmas. So that's moles of lead. And then we need to do the same thing for the uranium. So starting off with 1 gram of uranium-238, convert that to moles. And that's going to have a mass of 238 grams. .00420 moles. Because 1 atom of uranium-238 forms 1 atom of lead-206. 1 mole of lead-206 came from 1 mole of uranium. You can't say the same with the gram relationships because these are not the same element. If it's the same element, you're fine, but it's different here. So these are the numbers we're going to use. So how many moles of uranium-238 did we start with? We'll use this one. So we started with that. This is the number of moles of lead. What we want is how many moles of uranium are left. We have to subtract. This is how many moles of lead have been formed, which is equal to the amount of uranium that has decayed, right? So we don't want to put the 0.0007 in there. We want to subtract. Mm-hmm.
Could you do 0.000704 over the 0.0042 plus the 0.00704? So basically the lead over the uranium plus the lead.
I think you could, yeah. So could you take this and use that as how much? No, you couldn't. Because then you're looking at amount of lead out of, no, you can't. It's not going to be the same. So we've got this 0.002838 moles. That's how many moles of uranium there are now. And that's going to equal negative 0.693 over 4.5 times 10 to the 9 years times T. So natural 0.002838 divided by 0.0042. Did you get a different number? Yeah, I did something wrong there. Wow, and then I did something else really wrong on my calculator and got something. Yeah, I've got the wrong number up there. Dang it, I did it wrong again. It's time to go home. Okay, 003496. I don't know what I did there. Okay, that's wrong. And so this one's wrong. Oh, 3496. So natural log of 0.003496 divided by 0.0042 times 4.5 times 10 to the 9 divided by 0.693. Uh, 1.2 times 10 to the 9. That's pretty old. 1.2 times 10 to the 6th is a million, right? So this would be a billion. Any questions? This one requires more thinking than the carbon-14.
So in the book, I don't know if this is valid for the same question, but it has to where you take lead and you take it all the way to the grams of uranium, and then you add those grams of uranium to the initial that you had, so that would be 1 gram, and then you take that 1 gram divided by the 1 plus what you calculated from the stoichiometry.
Yes, you can do it that way too.
Do you feel this was easy?
Well, this is what occurred to me while I was standing here. Yes?
So the reason that we couldn't use the given mass ratio for our NO and NT is because they're 2 different elements, right?
Right.
But if it was even if it was a mole ratio, like let's say like instead of mass ratio, would we still have to go to like the respective molar amounts?
If it was a mole ratio, if it was 0.145 moles of lead to 1 mole of uranium, then the only thing you have to think about is, so then how many moles of uranium are left, right?
Because that would be what.
Because it's the moles of the original thing that are left divided by the moles of the original thing that were there to start with.
You still
But-
have to do the
You'd still have to do subtraction or do some adding or something. You can't just stick the numbers in. Because what you end up with in here needs to be proportionally related to, in the same way as the bottom one, the number of atoms present now divided by the number of atoms originally present.
So that's why the ratio is nice, but it's kind of like irrelevant because we need to see what the actual numbers.
Yeah, so, it's easy for them to say it this way, but it's not really very useful. Yeah. Carbon-14 dating, then it's useful, but not for uranium. Any other questions? The age of the Earth. So it kind of seems reasonable that the Earth is as old as the rocks that are on the Earth. And so they have found rocks that by these radiometric dating methods are over 3.5 billion years on every planet, every continent. The oldest one is about 4 billion years old. Now, is that an exact number? No. That is an estimate, okay? So based on this, they estimate that the Earth is about 4.5 billion years old. That is an estimate based on, you have to have some assumptions in there, okay? And then they estimate the universe to be 13.7 billion years old. I have my own views on how old the Earth is, but nothing to do with this. If you want to talk about it, I'd be happy to talk to you about it. We'll leave fission for next week.